Hello guys. Hello. Hi. I hope you're all doing well. So today we'll be going through our second video of Newton's laws. On the last video, we discussed forces on a flat surface. So today we'll be going through forces on an incline, but before we do that, also we'll be describing how forces work, and we'll be discussing different scenarios and how to tackle different scenarios while you're at it. So to start off, we're gonna start with questions which they ask on every time just before you go to calculations, which is the free body diagram. I know in the last video we spoke a little bit about this, but we're just gonna speak about it again and discussing other things maybe we could have left behind in the other video. So we said in the free body diagram, the mark there's always a mark allocation next to it, which shows you how many you need. So it shows the mark allocation shows you how many marks there are gonna be. I mean, how many forces there are gonna be on the free body diagram. So the mark allocation, you check the mark allocation, it will indicate how many forces you're gonna have. So that's what we discussed in our last video. So for example, check this one. It says so this one, it says draw a free body diagram showing all the forces acting on the block B immediately after it was released. Now if you can check block B here, block B, it has an extensible string on a pulley, and there's only two forces acting on it, which is the tension and the gravitation. And if you check the mark allocation, you can see it's 2 marks, so indicating that it's only two forces. That means you're only gonna have 2 forces. As I said, the mark allocation indicates the number of forces you're gonna have on an object. Now also, one thing we should note is that the free body diagram doesn't show it also helps you with calculations. So once you get correct the free body diagram, you're halfway through the calculations, because if they have the free body diagram right, that means you will know which forces to calculate, which forces not to calculate. Now, as you know, in the free body diagram, we have let me just pull the tablet. Okay, guys, so as I was saying, so in the free body diagram, you'll have many forces acting on it. And one thing you need to know about the free body diagram is that once you get, as I said, once you get the forces right, you're halfway through the answer. So now in the free body diagram, we have things like the normal force. We have things like the weight, which the weight you always get, no matter whether it's on a flat surface or whether it's hanging in the air, you always get the weight. And in some instances you won't get the friction because they will say it's on a smooth surface, which means if it's on a smooth surface there won't be any friction. But also others there will be on a rough surface, which means you will get the friction. So now I'm gonna start with as I said, the normal force. Now the normal force, if this is the okay, let me just do it like this. If this is the surface, the normal force, it's a force that acts perpendicular to the surface. So that means the normal force always acts. I gave the definition of normal force. It's a force that the surface exerts on an object, and it's always, there's that statement, it's always perpendicular to the surface. So that means the normal force always perpendicular to the surface, always perpendicular. So no matter if the surface is flat or inclined. So here, even if we have an inclined surface, the normal force always acts perpendicular perpendicular. So it's important to get this, because sometimes you can get this wrong, because sometimes you find people who are, you will have an inclined surface, but people want to put normal force like this. That's not how it works. Normal force always acts perpendicular to the surface. So that means if the surface shift is inclined, it's always perpendicular to the surface. So perpendicular, as you know, it has to form 90 degrees perpendicular. So you see here, it doesn't form what is it, 90 degrees when you put it like this, but in this way you have 90 degrees. So that's what it means, that it's perpendicular. It's the normal force. Normal force always acts perpendicular to the surface. Now I think we went through this when we were discussing the flat surface, that if I have a block on a flat surface, it doesn't matter, it's mass m, and I have the normal force. Obviously I will have the normal force, I will have the weight, and let's say it's being pulled, and sorry, and let's say it's being pulled. So it's being pulled, so we'll have the normal force as well as so we'll have the normal, we'll have the weight, and we'll have the force that's pulling, force applied, which it's pulling the object. So this will give mass m. Now what I'll explain, we are still discussing the normal force. Now in this case, when the object is on a flat surface, I think we also discussed this in that last video, that normal force, it's equals to weight. So which means it's equals to mg. In other words, normal force is equals to the gravitational force in this case when it's on a flat surface. But if we have an inclined surface like this, inclined surface, that means when it's on an incline, we'll have an angle here, and once we have an angle and this is being pulled, as I said, the normal force acts perpendicular. You can see I put it perpendicular, not like this. But the weight, the nicest thing, that's the nicest thing about the weight, is the weight always acts downwards. It doesn't matter whether it's on an incline, it's on a flat surface, the weight is always down. Whether it's on air, the weight is always down. So, and you don't have to, it doesn't actually like follow surface. Like in this case, the weight, it's straight down. I don't have to put it like the normal force, because the normal force I put it perpendicular, even the weight I have to put perpendicular. No, that's not the case. The weight you always put straight down, so the weight is always straight down. And we'll discuss as we go on, we'll discuss the components of weight and what happens with that. But what I want to show you here, in this case, the normal force is not equals to weight. So if you come here and say, if on an inclined surface you say normal force is equals to mg, you will get the answer wrong, because in this case the normal force is not equal to weight. It's only equals to weight when it's on a flat surface. So yeah, moving on. So moving on, we'll go to, let's discuss the weight then. Okay, now we're discussing normal force, let's discuss the weight. Now, before we move on, formulas for normal force. You have, I get it, for friction, you say friction is equals to coefficient of friction times the normal force. So in the same way, the normal force can be equals to the coefficient, friction over the coefficient of friction. But it's also equals to mg, in other cases not. So we'll discuss that. Now, the weight, which is equals to mg, which we have the mass, and we have the gravitational constant, which is our 9,8, and this is mass, it's calculated in kilograms, and this is meters per second squared. Now here we'll discuss, okay, So now on a flat surface, when you have a flat surface and you have an object here, and this is mass m, as we said, the normal force, and now we have the gravitational force. Now the gravitational force also always, we said it always acts downwards no matter where you are. So even if you have an angle and there's a block here and it's being pulled, this one is going that direction, you have your normal perpendicular, gravitation always acts downwards. And is it okay? Yeah, we have mass m as well. So now we're discussing, this is the weight. So we're discussing now, we're saying that in this case normal is equals to the gravitation, but in this, so now we're going to discuss gravitational components. So now when you're on an inclined surface, this only applies when you're on an inclined surface. When you're on a flat surface, it's straightforward. Gravitation is quite, it's mg, so normal is equals to mg. But when you're on a flat surface, that's not the case, because when you're on a flat surface, you have what you call components. We have what you call components of the gravitational force. Now the components will have a component acting downwards. So that means it will be acting downwards in which means acting perpendicular as well to the surface, the block, and we'll have one acting this way as well. So now this one, it's our fg cos of theta, and this one is our fg sine of theta. So this, it's others, it's also referred to, this one is also referred as gravity fg perpendicular, and this is referred to as fg parallel, because it's, this one acts it's parallel to the surface, and this one is perpendicular to the surface. So you have fg cos, fg cos of theta, fg sine of theta. So those form our, our weight. Those are our weight components, but only when it's on an inclined surface. Guys, get that? Only when it's on an inclined surface. When it's on a flat surface, as I said, it's straightforward. You don't even need to beat around the bush. You don't need to complicate yourself. It's straightforward. Just like that. It's straightforward. So now we'll move on. Now we are discussing our components, forces on a free body diagram. So we've discussed our normal, we've discussed our weight. Now we'll be discussing frictional force, our Fk. So now, as you know, as we mentioned later, frictional force is equals to coefficient of kinetic friction times your normal. We've also discussed normal. Normal is calculated in newtons. Coefficient of kinetic friction. Now guys, this has no units. So this is how you normally see if whether a number is a coefficient, or it's frictional, it's a coefficient of kinetic friction, or frictional force. This is how you differentiate. Frictional force is also calculated in newtons. So this is how you differentiate, guys, by unit. Frictional force has newtons on it. You will see there will be SI unit, newtons. But coefficient of kinetic friction, they have no unit. They will just write it. It will just be numbers, no units after that. Coefficient of kinetic friction doesn't have units. Only frictional force has units. Also, you find in some cases static, where the block is standing, it's not moving, where you have static friction, and you have times the normal as well. Also, the coefficient of static friction has no unit as well. So it's the same as this one, it has no unit as well. So that's how you see, that's how you know it's static, that's how you know it's a coefficient, when you don't see any units. Once you see units, it's not a coefficient. So when you see no units, then you know that it's a coefficient. So let's do this. Now, in our, let's say we have a flat obviously we're explaining, so flat surface, and we'll bring an inclined surface here, and you have an angle. Now let's put the forces. We've discussed the normal force, we've discussed the gravitational force. Let's say the object is going that way, and we have mass m, and because it's going that way, we know our definition of frictional force is a force that opposes the motion of an object. A force that opposes the motion of an object, and it's x parallel to the surface, right? So now this side, this one, our normal force. This is our normal force, this is our weight, this is our weight, this is your Fk, and this is force applied. So now, concerning our friction always opposes the motion of an object. So what you guys must understand, if the friction, it's quite easy, is that if the object is going to the right, friction is going to the left. If the object is going to the left, friction is going to the right. Now it's different when it's on air, because when it's on air, they will tell you to ignore air friction. So most of the time, especially when it's on a pulley as well, they will tell you to ignore that, and then so you mostly don't have friction in those cases. But when it's on a surface, whether inclined or flat surface, friction always opposes the motion of an object. So if the object is going to the right, friction goes the other way. So friction is that guy when everybody says, let's go this way, you'll be like, no, we are going that way, not that other way. So friction opposes the motion of an object. So that's how you get friction. Now we'll discuss that as we go further and go into certain examples. Now we're going to our fourth force, which is done. So now we have tension. Let's discuss the tension. Now the tension force, guys, it's also calculated in newtons, and the tension force, they like using inextensible string to show that there's tension. But when there's a rope, you see, when there's a rope attached to an object that has a mass, there will be tension. Now in terms of tension is, it's not that complicated. It only depends on the scenario. Sometimes you have scenarios where you have a block hanging, and when a block is hanging, let me just do this. Where you have a block hanging like this, and when you have a block hanging, you will have your weight acting downwards. As I said, weight is always there, it's always acting downwards. And instead here on the string, you will have your tension. This will be your tension, but we'll discuss the tension as we go further. So we know there's tension as well. Now let's discuss acceleration. So we know this formula, and I think we are familiar with it. And this acceleration is calculated in meters per second squared, right? And the mass, it's calculated in kilograms. Now guys, also be careful when you calculate this, because sometimes they may try to trick you and give you a mass in grams. Just know that you have to convert it to kilograms before you use it in calculations. You don't use a mass that's in grams when you are doing Newton's laws calculations. You don't use a mass that's in grams, but you use it in kilograms. So if they happen to give you a mass in grams, you immediately convert it to kilograms before you can use it in your calculations. So now, there's a statement that they usually write, and you will see once they write this sentence in a statement, they will write it in capital letters like this. They will write whatever they are writing, and then they will say constant, and then they will just say speed. You see, so once you see the word constant speed, already what should come in your mind is that once I see constant speed, it means this guy acceleration is equals to 0. So whether they say constant speed or constant motion, so once they say constant speed or it's moving at a constant motion, just know that your acceleration is 0 meters per second squared. Just know that this guy is 0. Only when it's moving constant, because when it's moving constant speed, there's no acceleration to it. It's moving at a constant speed, constant velocity. They can mention them, but once you know, and they usually just write it in capital letters to highlight it. So guys, once you see constant on a statement, just know that already we are working at an acceleration of 0. So that's covered for acceleration. Now let's discuss our forces. So let's do a free body diagram. Okay, no, let's have a scenario. This is being pulled. Okay. Okay, so let's say we have an object. Let's say we have an object that's been pulled. So we have our normal, we have our weight, we have mass M, and we have force applied, and we have our kinetic friction here because this block is moving. So they tell us that let's say they tell us that the block will switch. Oh no, sorry, the block is moving to the right, and they tell us that it's moving at a constant velocity, and then they give us the force. Okay, that there's 50 newtons force applied to it. Now guys, important thing while doing newtons as well is that you should never mix your forces in calculations. By this I mean, don't mix your horizontal forces and your vertical forces on the same calculations. Here's what I mean, especially when you're working when you're looking at one block. For example, if I only have one block like this, and it's on a flat surface, and they gave me 50 newtons, and then they told me that it's moving at a constant speed. So that means I know my acceleration is 0. And let's say they give me mass of 2 kg. And once I have this, and then they tell me to calculate my what is the amount of the frictional force. So, and then I say Fnet is equals to MA. So that will be my force applied. Guys, remember, once, and also when you do calculations, you must always remember to choose a direction. So choose a direction. For example, it's either you choose the motion of an object as where the object is going at as the positive direction, or maybe as the negative. So if I choose where the motion is going, which is to the right, as positive, that means I can't put negative force applied. I have to start with force applied and then say minus friction. So I can't say minus Fk minus force applied if I'm choosing right as positive, because if I'm choosing right as positive, that I'm saying all the forces that are going to the right are positive. and all the forces are going to the left are opposing, which means they will be negative. So I'll have F applied minus Fk, which is equals to MA, and this will just be my 50 newtons minus my Fk. My mass will be 2, but by acceleration it's 0 because it's at a constant speed, so I'll have 0. I will take this Fk, then I will have, so I will have, and then I will just calculate, get my F, what is it, get my kinetic friction and all that. So this is what I'm saying. These are my, but you see I used Fa and Fk because these are, remember this is scenario I made up. So because, but I use, what I'm trying to show is that I use this because these two are my horizontal forces, and I was calculating Fk, and frictional force is one of my horizontal forces. It wasn't on a what is it, it wasn't on a vertical surface. It's not vertically, it's horizontally, so I can't use my vertical forces to find the horizontal forces, unless, let's say, I had a coefficient of friction. If I had a coefficient of friction maybe 0.25, it's my coefficient of friction. Then let's say I had my, and this, in this case, your normal force will just be equals to your weight. So then I will have my Fk equals to my coefficient of kinetic friction times the normal, which will be the 0.25 multiplied by your mg, which is, you will be your 2 and 9.8, because my mass my mass is 2 kg, so which will be your 2 times 9.8, and then you'll get the answer. Now what I'm trying to explain is that you don't say, this is what I explain, you don't do this. You don't say okay, Fa minus Fk, and then you decide to say minus weight is equals to Ma. Already if you do this, we're like, okay, where is weight, which force do you see any weight force on the vertical things, on your vertical side? If not, why you don't put it? So you must, that's why the free body diagram helps. So if I was to draw a free body diagram for this, I'll show you. If I was to draw a free body diagram for this, it will be my normal force, it will be my gravitational force, it will be my force applied, it will be my kinetic friction, it will be weight, normal. So this just shows that already I have horizontal forces, I have vertical forces. So don't mix the two. Don't, when you are including in your horizontal force, calculating horizontal force, and then suddenly you put one of the forces starts in the horizontal and mix it up. So don't confuse the two. Now we're gonna, I'm gonna show you we're gonna go through few scenarios, just few scenarios. We're gonna be skipping through scenarios, so that means we're not gonna be doing the whole question. So this will just be to emphasize what I just said. Okay, let's start on a flat surface like this one. So here it says grade P of mass 1.25 kg connected to another grade Q of mass 2 kg by light inextensible string. So you guys taking notes. The two grades are placed on a rough horizontal surface. Remember I explained this. When it's a smooth horizontal surface, you don't have friction, kinetic friction. I mean, actually you don't have friction. There's no friction at all. So when it's a rough surface, that means we have friction on it. So already they didn't even tell us about anything about friction, but already from reading that it's on a rough horizontal surface, you already know that there's friction included in there. We haven't given anything about friction, but we already know that. And then they say it was connected by light inextensible string, so we know there's tension there. And then it says a constant force. You see, in this case, they didn't highlight the constant, but most of the cases they do. They just write the constant in capital letters. Oh no, it's a constant force, sorry. So yeah, no, it's not. They didn't say it's moving. Okay, so it's a constant force of F of magnitude 7,5 acting at an angle theta to the horizontal. They didn't give us the angle, so is applied on grade Q as shown in the diagram below. The grade accelerates is 0,1 meters to the right. So yeah, because they said, they didn't say that one will explain it's constant speed, constant motion, or it's moving at a constant speed or constant motion. This one they just said it's a constant force. So it's a constant force to the right, but doesn't really mean acceleration. Your acceleration will be 0. As you can see, they say the grade accelerates at 0,1 meters per second to the right. So they've already told us where the grade is going. Now, if we look, the statement is not done. They say grade P experiences a constant frictional force of 1,8 newtons. So, and then grade Q experiences a constant frictional force of 2,2. So grade P has a frictional force of 1,8 newtons. Grade P has 2,2 newtons. And I think, guys, you can differentiate because grade P is much smaller than grade Q. So you can even see in the magnitude of your friction that it's not the same. Now, here they're asking us to draw a labeled free body diagram for grade P. So I'll draw for both. So let's start with grade P. So in grade P, you have simple, which is your normal force acting downwards. You have your weight and to the horizontal, and also they also told that there's friction. So this is your kinetic friction, guys, but this one is not force applied. This is my tension because it's connected with an inextensible string to grade Q. Now let's draw a labeled free body diagram for grade Q. Grade Q will also have so you have your normal, you have your weight. Now here's another thing. You see this one, the force, it's at an angle, guys. So once they give you a force at an angle, don't do your own things and start putting force on a straight line like it's things parallel to the surface. As you can see, this force, it's at an angle, so you must, even on the free body diagram, you must show that it's acting at an angle. You must show that it's not straight, it's acting at an angle. But my frictional force, it's acting straight. So you have your frictional force and this is your force applied. Only if I was, remember on the free body diagram, if I was using, because force applied also has components. Once it's at an angle, it has components as well. So if only, I could only write it straight if I was using my component. So if instead of writing force applied on its own, I would write this. So this will be my Fx and this will be my Fy. So if I was, sorry, I didn't. Sorry guys about that. So as I explained, let me go back. Now for block P, we have this. For block P, we have our normal, we have our weight, we have our K, we have our tension. It's connected with a string to block Q. For block Q, we have our kind of friction, we have our normal, we have our weight, we have our force applied. Now if you're only using force applied, you write force applied, you write it at an angle because it's given at an angle there. So they don't, if they give it to an angle, you also in the Fibonacci diagram indicate that this thing is not just straight, it has an angle. You don't know the angle, but still. So I could also write in terms of its components Fy and Fx. Now, if you write Fy and Fx, you don't write force applied. But if you write force applied, you don't include Fy and Fx. So two choices. So yeah. So now you can see, okay, on the question they ask us to write only a free label diagram for block Q. So if you check block Q, if you check the allocation marks, it's 4 marks. So basically after I've written this, it's 4 marks. So I'm gonna get 1 mark for normal, one for this, one for this. It's your 4 marks. 4 marks, 4 forces. Guys, remember you must also label. Don't forget, they said draw a labeled free body diagram. They already say a labeled free body diagram. They didn't just say do a free body diagram. So don't forget to label your free body diagram. Now let's come to this scenario. So in this scenario, they say 2 blocks, A of mass 4 kg and B of mass 10 kg are connected by a light inextensible string. The blocks are held at rest on a plane which is inclined at an angle of 35 degrees to the horizontal. Now they say constant force F acting parallel to the plane is applied to the block B as shown on the diagram. The blocks now accelerate up the plane 2 meters per second squared. So we have acceleration as well. Obviously the first question will say state newtons. Yeah, now let's discuss what we have. So here they told us that we have our acceleration at which is 2 meters per second squared. We have acceleration which is 2 meters per second squared, and they told us that it's going up the incline. And so let's start with free body diagram for our 2 blocks. So let's start with the 4 kg block. It's on a surface, so there's normal force, because normal force is the force that acts exact force on the object, like a surface that acts on an object. But one thing we said about the normal force is that it acts perpendicular. So remember, even on an incline, still perpendicular, it doesn't matter. So when you in your free body diagram, you must show that this is on an incline. So you mustn't write it like this even on an incline. You'll get it wrong, because this is not how it is, because it acts perpendicular to the surface. If it acts perpendicular to the surface, that means even on the incline, the surface is on an incline, so that means it's still perpendicular. We want this 90 degrees because it's perpendicular. Now the weight, just write it as I said, the weight always goes straight downwards. Now they told us about the frictional force as well. Now frictional force acts parallel to the surface, and here guys, the surface, this is our normal, this is our weight. The normal is on an incline, so you don't write your friction like this. You will get it wrong because it's on an incline. So even on an incline, so you follow the surface. If the surface is like this, whether it's like this or like this, you follow the incline. You follow the surface. So if the surface is on a straight, it's easy, you can write it for straight. But if it's on an incline, Also, your forces must show that they are not on a straight surface, they are on an incline. So this is my force applied. So this was for block A. Now let's do for block B. Block B also we have our, oh, sorry, my mistake. This is not force applied. Because block A is connected by an extensible string, so that's my tension, not force applied. Sorry about that. Now this is my normal, this is my weight, and obviously my FK, my kinetic friction, and this will be my, yeah, then this will be the force applied. As you can see, they are like this to show that it's on an incline. You can see they are not straight. I didn't put them straight because it's on an incline. Also on this, on block B, we don't just have the 9 kg block, but we also have the, oh, I think on the other one, when I did the free body diagram for this one, I forgot to include the tension. So my mistake, guys. So here, remember, when there's tension, I get on the other one you write tension. That means here there will be two forces. It will be the FK, and there will also be your tension. So if they ask, if they were gonna ask me for free body labeled free body diagram for the block A, which is the 4 kg block, they will give me 4 marks, and for the block B, that will be 5 marks. Because block B, I have 5 forces. So it's my tension, it's your normal, it's your force applied, it's your kinetic, it's my weight. Here it's only weight, kinetic, tension, normal force. So guys, now, but already you can see from, you can also already see from my free body diagram. I haven't even calculated. I haven't even looked what question what they're asking me to calculate. I haven't looked at the kind of questions they're asking me, what they're asking me to find. But already I've done this, and what I've done is, it means I already know the kind of forces I'm working with. This is on an incline. You said you have components of weight. So there's another option which you can also, the same as when you are doing the force, the same as I show you in the force applied, you can also write this, which is your FG parallel, and this is your FG perpendicular. But guys, once you write FG parallel and FG, once you include FG parallel and FG perpendicular, obviously when it's on a free body diagram, you won't include it like this. You won't include this FG perpendicular like this. You will include it here. You will include it here. Sorry. So you will include it here with your fraction, and then you just say FG parallel. But once you do that, you don't include your weight. Once you do that, you don't include your weight. It's either you just write weight or you just write the components. But once you write components, you don't write the weight itself. Hope I'm clear on that, guys. So now, if drawn the free body diagram, you see for block A, as I said, show it has 4 marks, showing us that it's 4 marks, shows that it has 4 forces. Now check out this question. It says the angle that the plane makes with the horizontal, which is question 2.4. So it says the angle that the plane makes with the horizontal is now decreased. How will the change in kinetic friction force acting on a block? How will this change the kinetic frictional force acting on block A? So in this case, guys, so let's go back here. So they're asking us that, they're telling us that they now decrease, what is it, the force. I mean, not the force, but let me just, pull that up. So they're telling us that now they are now what is it? They are now decreasing. They are now decreasing the angle of the incline. So I think, but generally speaking, when you're on a steep slope, and going down, it's much easier. I think, you know, for even boys, when you ride bicycles, we love once you reach the incline slope, because you know you can stop, you know, cycling. You can just sit there and then you let the bicycle ride itself, which I think is concept here. So when it's on a steep slope, goes faster, right? Now, but here the question is, what will happen? How will this change the kinetic frictional force acting on block A? Oh, they ask us about block A. So, okay. This is the case. So we had originally we had 35 degrees, and let's say here now it's 15 degrees, and let's literally do another one and say now this is 45 degrees. We now increasing angles again. Oof. Sorry guys, it keeps disappearing. Oof. So okay. So now let's read the question again. The question says, yeah, the angle that the plane makes to the center is now decreased. How will this change the kinetic frictional force acting on block A? Yeah. So now let's check this. Already here, guys, we can see that this thing is being pulled up. So let's say, imagine you're pulling something on a steep slope. I mean, when you're pulling something on a gentle slope, it means on a flat surface, it's much easier to pull, right? But once it's a steep slope, that means you have to be there, you'll be there dragging. So it's much harder on a steep slope to put it on a steep slope. So they're asking us what will happen if they decrease. So if we take the angle to let's say now we're now taking the angle to 15 degrees. If you take the angle to 15 degrees, that means it's closer to the flat surface. That means it's like you're coming closer to flat surface. So if you are, it's closer. So that means it will now be much more easier to pull. It will be much more easier to pull. That means if it's much more easier to pull, you will even pull it at a what is it? At an extended speed, at a certain speed, at a more speed. So it means that if your speed increases, that means your friction will as well. And if it increases, if your angle increases, same thing as well. If your angle already, if it was hard pulling at 35 degrees, if they increase the angle, then you also realize, like, now you're carrying something to climbing a mountain. You realize how hard it is. So now, but if this thing was going down, that would be a different thing, because if it was going down, the more you increase the angle, the more faster it will go. But now we are pulling up, so because we are pulling up the slope, the more you increase the slope, the more harder it becomes. So now they ask us what will happen to the kinetic friction. Easy, the kinetic friction will increase, because why? It will go down. Easy. I'll show you. Okay, so okay. Now, because it will be much easier. So now, kinetic friction will increase because now it's much easier. That means you'll be able to pull it faster. So already, if you start pulling something fast, that means your friction will be fast, it will be more as well. So because you're increasing your force, so it will be more. But once you extend the angle, same thing. You extend the angle, you decrease. Once you extend the angle, it means you will decrease the frictional force. So Now let's check this one out. Okay, I hope it's like we don't have time to go through the other one, but let's just cover this one. And if there needs more, we need more clarification, we'll do another video on mutons, but it'll just be touching. Next week we'll be doing video on another topic, but I will inform you in terms of that. So let's go through this now. Here the block, 2 blocks hanging on a pulley. The other one is 7.5 kg. The other one, the mass is not given, but you can already see that the other one is smaller than the other one, and it's above the ground. They say when block B is released, it moves vertically downwards. So block B moves downwards. So once block B moves downwards, it means already you can see that it means block A will move upwards. And once that happens, this one, it means will touch the ground, and this one will be somewhere in the air. It will stop somewhere in the air once 7.5 reaches down. And it says it strikes the ground with a velocity of 3.41 meters per second. Now guys, let's start with what we're discussing. Free body diagram. Free body diagram for these 2 blocks. If you're doing free body diagram for these 2 blocks, so for block A, it will be straight up, which will be your tension, and it will be down the ground, which will be your weight or your gravitational force. But that's, I'm thinking from this, you can see that you can already see that in here we only have 2 forces. We only have 2 forces acting in this block, so it's much easier. We only have tension, we only have gravitational force in both and you have that in both blocks. So already that means you'll be working with this. Now to go back to before we close, to go back to the incline. So as I was saying, let's say we are on an incline. Oh, can be that on an incline, sorry. And this is our normal, as you said, and this is our weight. And let's say we have that one, we had FK. Sorry about that, guys. We have our FK, FG, I mean, sorry, not FG, FK, which means our kinetic friction, and we had our tension. That's for the first block, the block which was pulling, the head which was pulling, and this we had our force applied. This is the free body diagram we had, right? And if now I have to resolve this in terms of components, it means resolving my horizontal and my vertical components. Just want to explain the exercise that my force applied will be here, so it will be let's just put them there, plus tension plus Fk is equals to Ma. This will be your F net. F net, it means it's all the forces, so Ma. Now in terms of writing them with, now we are writing signs. Fa is going one direction, tension and friction are going the same direction but opposite from Fa. So that means that will be minus tension minus, why did I write Fg here? And then Fk, so that will be Fk is equals to Ma. So this will be my horizontal component. Now, oh, I see I made a mistake here, guys. Okay, sorry about this. But also I will have plus my Fg parallel. This is on an incline. So remember, we have your FG parallel. So now in terms of FG parallel, let me show you. Let me write them as I did. It's FG perpendicular. So guys, in terms of knowing whether your FG parallel goes downwards or upwards, this is how I do it. So after I draw the weight first, and after drawing the weight, I know the space that will be left, it means the one that will be perpendicular, that will be the same. It means perpendicular to the surface, perpendicular to, that means that will be the same as the normal force, which is this one, FG. And then I start with the FG perpendicular, and I know that the space left to connect this, so this space left to connect these two, that will be my FG parallel. So that means I already know that my FG parallel will go this way. That's how I do it. So now already it means it will go with tension, friction, and it will go with tension and friction. So that means I already know that it's going in the other direction, opposite. So that will be my mg sine of theta is equals to ma. Sorry, that will be my mg sine of theta will be equals to ma. So guys, yeah, and so that's how you tackle, and pretty much everything revolves around the concept that I've just said. If you see, once you understand this concept, once you understand everything like this, it means getting into examples will be much easier. I think we'll do another short video maybe next week before we go into the other one about with different actually going through these examples and explaining. Obviously now we've covered the concept and the tips on how to do them, but next we'll do examples. So guys, yeah, thank you for watching, and yeah, see you next time.